The fire environment triangle includes all the things in the environment that influence fire spread and behavior patterns in nature. Fuels, weather, and topography are the primary factors that influence how hot a fire gets and how fast it spreads. In addition, fire is included in the center of the triangle. Fire itself can produce positive feedbacks that further influences fire behavior. This video focuses specifically on fuel, how it is characterized, and how it influences fire behavior. Fuels are defined as organic materials that burn in a fire. In a wildland setting, this can include trees, downed logs, shrubs, grasses, litter, or duff. Fuels in this photo include all living and dead plant material above mineral soil. However, not all of this fuel is necessarily available for combustion. For example, the tree needles may be too wet to ignite. The large logs may also be difficult to ignite under certain conditions. Available fuels are those fuels that are available for combustion at any given time in any environment. Fuels can be classified as ground, surface, and aerial or crown fuels. Aerial fuels include foliage and small branches in the canopy of trees and tall shrubs. Surface fuels include litter, downed wood, herbaceous plants, and small trees and shrubs that are on or near the surface of the ground. Ground fuels are fuels that are below the surface and can include duff, buried logs, roots, and other organic material. Surface fuels are used in fire behavior models to describe potential surface fire behavior. Surface fuels and aerial fuels are used in fire behavior models to describe potential crown fire behavior. Some ground fuels are used in fire effects models to describe potential fire effects on soil, vegetation, and air quality. The rest of this video will focus on properties of surface fuels and how they influence fire behavior. Wildland fuels have very different properties that can influence fire behavior in different ways. These specific properties are often quantified so that we can have some understanding of potential fire behavior. Let's explore each of these fuel properties a little more. The amount or quantity of fuel in an area is expressed as loading in tons per acre. Fuel loading is essentially the dry weight of fuel in a given area. In the photos here, we can see a grassland fuel type with low fuel loading and a slash fuel type with high fuel loading. The greater the fuel loading, the more heat will be released when the fuels are burning. However, greater fuel loading may also lead to slower rates of fire spread. The size and shape of fuel is expressed as the ratio of surface area to volume. Small fuels, such as needle litter and grass blades, have large surface area relative to their volume, expressed as surface area to volume ratio. Fuels with high surface area to volume ratio are relatively easy to ignite, thus can contribute to rapid fire spread. The depth of the fuel bed is measured from the soil or duff surface to the top fuel layer. Fuel bed depth will influence the length of flames. The deeper or taller the fuel, the higher the potential flame length. Compactness can be defined as the spacing between fuel particles. Compact fuel beds have little spacing between fuel particles. Fuel compactness is expressed as the packing ratio, which is calculated from fuel bed depth, loading, and size. Fuel beds with a high packing ratio are more compact. Compact fuels have little oxygen available for combustion, which makes them more difficult to ignite. The long needles of ponderosa pine make for less compact fuel beds compared to the short needles of pinyon and juniper trees. Thus, ponderosa pine litter tends to ignite and burn much more readily than pinyon and juniper litter. Another important fuel property is arrangement, which is the dominant orientation of the fuels. Fuel beds can be arranged either vertically or horizontally. Grasses and shrubs are vertically oriented, while timber litter and logging debris are horizontally oriented. Vertically oriented fuels will tend to have longer flame lengths compared to horizontally oriented fuels. Fuel beds can also be described as being either continuous or patchy. Patchy fuel beds have fuels interspersed with areas of no fuel. Continuous fuel beds have few areas with no fuel. Fire is more likely to spread through continuous fuels. Some fuels have high amounts of volatile substances such as oils, resins, waxes, and pitch. Examples of such fuels include many shrubs found in chaparral systems and palmetto, which can be found in southeastern forests. Fuels with lots of volatile chemicals in the leaves can be easy to ignite, even with high moisture content. Finally, the moisture content is one of the most important fuel properties that influences potential fire behavior. Fuels with high moisture content are difficult to ignite. As you can see, there are a number of properties that influence potential fire behavior, some of which are difficult to measure. To aid managers, several fuel models or standardized descriptions of fuels have been developed. These fuel models describe typical values for a variety of fuel properties from different vegetation types. Rather than measuring fuel properties in a given area, these fuel models can be used to determine potential fire behavior under a variety of conditions. Fuel is an integral part of the fire environment triangle. Thus, understanding fuel and its properties is vital to understanding how a wildland fire might behave. This knowledge also informs strategies for manipulating fuels to influence potential fire behavior.